you.
Okay.
Okay?
Okay, got it. Thank you.
All right. I think we can slowly start getting okay, you guys are complaining about the grades not coming back. Again, we're learning that you have to keep track of which email you send it from and what is the format. And then we had Word format, we had PDF, JPEGs, and so maybe this next exam we're going to streamline it a little bit more. That is the problem. Anyway, those that were very eager to know what their grade is, I was able to email them back. All right, let's move on because semester is getting to an end and then we need to cover the material. That's life, you know, we have to finish what we've done. All right, so let me start with the class. I think you guys should start, you know, with the chat getting unhappy about not receiving the grade. You'll get it eventually, so don't be so unhappy about it. Okay, let me see, where is that share? All right, here we go. So we actually did the cylinder, flow over a cylinder, and hopefully we're going to end up with some understanding of the drag in fluid mechanics. That's where we're going. We did solve the problem with frictionless flow, and there was also a nice example of how can you take existing solutions, combine them in order to fulfill the boundary condition. And this is showing how you get solutions like that. So in my second note, I said that we actually not solving, we just trying to get a combination which fulfills the required boundary condition. So that's how we got the doublet pointing into the flow and eventually ended up with a circle with a streamline which looks like a circle, but there's no flow through it. Therefore we said, oh, that's a flow over a cylinder. Also, I mentioned that that's the simplest case to demonstrate in class, which looks like something realistic. And that's why we did that. If we could solve things for like a flow over a streamline shape, then experimental result would be very, very close to what we get here. But class is really short, and then we cannot spend too much time on solutions, which will take a lot of time. Again, aerospace students will have 301, which is an extension of that thing. Okay, so we, at the end of the day, we're really looking to understand the drag mechanism. Okay, so I'll just very quickly go over what we did last time. So we took a doublet, we turned it around. Remember, before the doublet was pointing to the X direction. I think somebody said that you want full screen. Okay, let me get to full screen. Okay, full screen it is. So before the doublet was pointing here, but we turn it around, so it blows into it, and at a certain point, the velocity stops because the velocity goes down at 1 over r from here, and here the velocity is constant. So at a certain point, we got zero velocity, and then we hope that there's going to be some streamline which will go around and going to look more like a circle. So that's what we did. That's the free stream, okay, which is u infinity x basically. And then here's the doublet with a plus sign because it's pointing to the other direction. And that's the combined velocity potential in cylindrical coordinates. We did that, and then you can move to Cartesian, but it's much more convenient to use that coordinate system. Then we looked at the velocity in the radial direction, and it had a plus minus sign. So we tried to make it equal to 0 And turns out that when R is equal to a certain amount of mu, then we can get zero normal velocity. So we replace that mu, and eventually we end up with this formula. So QR is a velocity inside. Let me just get the pen before it jumps away. So QR will be the velocity anywhere here, any direction. Okay, let's say here, QR, you're gonna have QR, this thing. But once the radius goes to this capital R, which we call the radius, then it becomes zero. And then again, it develops, and then there are radial directions. So for example, here the radial direction keeps on, eventually becomes the same as the free stream here on the x-axis. Okay, close to the x-axis. So that's what it is. So eventually that will be the velocity potential just by replacing the mu. And that's the nicer way of showing the velocity potential. And these are the resulting streamlines. So we did it last time. So that's the potential flow solution about a circle, okay? And we also said that the points inside are really, these points are not taken into account because that's an inner flow. We're just looking at the outer flow, which looks pretty good to us. And then we try to see what's happening. Basically, trying to figure out what is the pressure, what's the lift and drag. So what we're trying to do is looking, oops, I touched the mouse, it's gonna jump. That's what it did. Okay. So we're trying to figure out what is the pressure along this line. Okay, so all we need to do is say R equal R. And here's the velocity q theta, for example. And then, of course, the radial velocity is going to be here. Here are again the numbers. So if you're going to put R equal R, capital R, then we end up zero, as I tried to convince you before, on the radial direction. But tangential direction, we get this. It's 2 times u sine theta. So it starts from 0, goes up, and is a sine and come down very much like that. So that's a sine shape. And then we're applying Bernoulli, because now we're going to find out what is the pressure distribution. And then we take a point somewhere at infinity, here. And then we take an arbitrary point on the surface, And then what we do is just take p minus p infinity and then move this to the other side. Instead of q theta, we substitute 2u infinity sine theta. And this is, of course, square, so we end up this. This is the pressure difference. Again, it varies like sine. And Cp, we define the pressure coefficient, which is the pressure difference. And then what I pointed out, that if sine theta is 0, it's actually 1. And then it ends up with a minus. So if you try to plot that, and there is a 1, 1, 0, minus 1, minus 2, and minus 3, then this behaves very much like it's a sine sign. Sine, and this would be the pressure distribution somewhere here. Something like that, okay? And actually it is plus here. So there is pressure, which you're gonna see in the next slide. So the result, again, this is Cp. The results are that there is pressure here. It's pushing on into it. Here there is suction in this region, and here it's actually equal to the free stream. And this is the solid line is the exact solution. This is that formula right here. And then I just mentioned here, this is some generic remark, that if you try to figure out Cp and you have a local velocity, it doesn't matter which case, then it's 1 minus velocity over free stream. And that's very nice to show that at the stagnation point, when the velocity is 0, you get Cp equal 1 automatically without thinking too much about Bernoulli. So that formula, this one, is kind of good to recall. It's very, very useful. Okay, so then we're looking at experiments. And again, experiment depends on Reynolds number. I will go to that in a minute. Okay, but in general, the flow separates, so it doesn't do that. It starts like that, and then it's a little bit less than this, but here in the back, it stays negative. Why? Because the flow doesn't follow, it just separates somewhere. Separates, therefore we get a flat pressure behind, which is negative. As a result, in real life, there is plus pushing back, there is suction pulling back, so there is definitely drag. There's a drag, which is significant drag. Okay, and that was called the D'Alembert paradox. And okay, so one more time, there is symmetry for an F. I mentioned that stagnation points are here. Here's the stagnation point. Oops, I touched it again. I need to get the pen. So there are stagnation points here and here. Again, here's the pressure distribution, which we mentioned. Velocity distribution is actually twice the free stream, and it's -3 in terms of CP. So you have to get used to the CP, or else you can use velocity. So it's going to be 0 here and 3 times the velocity here. Okay. And we're looking at the solution. There's symmetry up and down and left and right. Therefore, naturally, if you do the integration of the pressure around it, and then we define pressure, which is, or integral of pressure, which is acting up, we're going to call that lift, and which is resisting the motion or against the flow, we're going to call drag. So R d theta is the element, pressure is the local pressure, which is substituted right here, and then R, and then sine theta is the direction, and cosine theta is for the drag. And then we do the examples, and then, well, it comes out 0. Of course it comes out 0 because this is symmetric. So there's no rocket science here. And so, okay, so before I start complaining about the solution, we solved the velocity distribution over the cylinder. Here it is. And this is what we ended up, the CP 1 minus sine squared 4. But turns out that you can actually get a solution for the same problem over a sphere using spherical coordinates. And it's very similar to that. It's again sine square. The only difference is the coefficient. Why? And then here's the plots. And the reason is that in 3-dimensional flow, the flow can go around on the sides, and therefore the suction or the increase in velocity, which is the same thing, is going to be less. Okay, so again, if you have a 2-dimensional case and then you're trying to do the 3-dimensional case, the pressures are going to be less and the velocities are going to be less as well. Okay, so it's the same thing. So that was the objective. So now we have to actually look at the reality and see what happens. So I mentioned that in real life, the flow separates, and actually there's no fore and aft symmetry. The front tried to behave very much like we did, but at that point, the flow separates, it doesn't want to come back. Okay, so it separates, and therefore the pressure inside in the back usually is very close to the pressure at that point, okay, because it's kind of a big separation area. I mentioned D'Alembert that wasn't happy about it 200 years ago, and he probably would have been unhappy today as well. But he solved the potential problem and did not solve the actual viscous case, and he did not understand that the drag is actually due to flow separation, not just viscosity. And anyway, so he didn't understand that very well. To this day, it's called D'Alembert paradox. Then I tried to get some rationale. Okay, so if we were able to solve the flow over a streamlined shape, like I'll show here in the upper case, okay, then the CP, and if I want to show the velocity is going to be the same thing. I have to put the scale here of, let's say, instead of, it's going to be 0, and it's going to be, let's say, 2 times the speed of the free stream, u infinity. Okay, so that diagram would look exactly the same in terms of velocity. Why? Because Cp is 1 minus u over u infinity squared. So it looks very similar, but it's upside down. So the velocity is going to be positive, always positive. Here it goes from plus to minus. Anyway, when you get used to it, it's very logical. When you're not, then kind of disturbing. Anyway, what I'm trying to convince you is that the velocity increment are kind of following the shape of the object. So velocity stops, high pressure, accelerates, low pressure, low pressure, low pressure, and then tries to recover. Hopefully the pressure come back to 1, but usually it does not come back, usually come back to the free stream. Similarly, I showed you the car. If you have stagnation coming in, high pressure, which is this point, and then acceleration, so minus again, which is high speed, then a concave section, so the flow slows down, and then convex section, velocity still accelerate. So I'm trying to convince you that you can actually look at an object and kind of figure out just visually where you would expect high pressure and low pressure. Okay, that's the whole reason behind me explaining it twice. And then, okay. Then I gave you that example, and I keep on showing it. It's at Reynolds 10 to the 5th. The drag of the little sphere is the same as the airfoil. Why? Because the drag here is a result of skin friction mainly. This is skin friction here, boundary layer, while here you have flow separation. And then we have the high pressure here at CP1, and here at CP minus something. So just to show the magnitude, how large the effect of flow separation compared to the skin friction. Okay, I think this is somewhere where we stopped. And I'm emphasizing what I just said is that the mechanics of drag, there are two reasons for the drag. One is skin friction, which we showed the boundary layer. And again, in the shape of the very streamlined shape, that is the main component. So that's the main component of stream friction. However, if there's flow separation, like here in the case, in this particular case, then the main components is going to be flow separation, which is right here. So there's a big minus pressure here, and there's a big cross. And anybody asking a question, or you just talking locally? Okay, it's probably you guys talking locally. And then I'm just here emphasizing again what I told you before, that it would have been nice if I could solve that in class, and then say, hey, it's exactly like an experiment. But that is more complicated. I could solve that fairly easily in class, so, but it doesn't compare, but it still gives the message. Now, historically, that problem, the sort of flow circle, was solved first, okay? But there was a gentleman in Russia by the name of Zhukovsky who invented a transformation from here to a flat plate, or even an airfoil at an angle of attack. And then he solved the problem of the flow going around an airfoil and creating lift by just taking that solution and transforming it to the other plane. So that would be an analytical solution. We could have done it in class, but it's complex variables. And I'm not sure if you're going to enjoy, I would have enjoyed it. Okay, so now let's look at that in the range of Reynolds number, within the Reynolds number. So what I told you is high Reynolds number, but let's just look at that more carefully. So we take a cylinder, okay, and put it in Reynolds number, like in in oil, very greasy oil, let's say Reynolds number is less than 5, so it's pretty viscous oil, then the streamlines are going to be amazingly close to what we got, very close, but for the wrong reason, because that's a viscous flow. That's a viscous flow. So now you start increasing the flow to 15, let's say, anywhere from 0.5 to 15. So increasing, one way is you just increase the speed, the other way you change the viscosity of the liquid. And then you will start getting separation, and the problem is symmetric, up and down. There is symmetry in the problem. But once you start going up to Reynolds number of, say, over 40, then you start getting vortex shedding. Now, remember I told you the story about boundary layer, that you have a shear here, and then you create little vortices, and then eventually there are too many vortices inside, and then they start giving velocity to all kind of direction and the flow transition. So similar thing. Initially, this is laminar flow. You get too many vortices from here and here, and then they grow. They just cannot sit together. So they start alternating, go left and right, and you get this thing which is called the Kármán strip, the vortex shedding. Okay, and it keeps on growing, and then 150, 300, you don't see much difference, but if you look at the wake or the vortices in the back, they're starting to generate turbulent flow behind them. Okay, and then I say you start getting to what we call high Reynolds number range, which is say 10 to the 5th, then the boundary layers start getting turbulent on the surface. If the flow is turbulent, remember there is momentum up and down. So the flow will separate actually later, because fresh momentum comes from the outside of the boundary layer. So if the separation point was here in the lower Reynolds number, now the separation is here. So amazingly, the drag gets lower. You get less drag. And then later on, the whole thing becomes fully turbulent, and the wake shedding continues, and it's more messy a little bit. And here are some velocity or pressure distribution for the different cases. Okay, so we need to remember that the scenario roughly versus Reynolds number. Now, experimental data. So the drag coefficient, the drag coefficient is, we in the same phase as we did the pipe flow or we did the boundary layer, we did some model and say, okay, let's look at the drag or the skin friction or whatever, the pressure drop in the pipe versus Reynolds number. So it's the same thing. And turns out that the solution of Stokes, which is for the sphere, which I mentioned, this is a viscous flow solution, okay? It gives you 24 over Reynolds, which is exactly this curve. This is 24 over Reynolds for the sphere. Okay, so this is analytical, but we need to solve the viscous flow. Lots of algebra, we kind of skipped that in this class, but this is what you get. Eventually, the flow becomes turbulent, as I mentioned, and the shape kind of plateaus here. These are some of the experimental points. And then when suddenly the flow becomes fully turbulent, like here, okay, so the separation goes from here to here, okay, from here to here, okay? And then this is called the critical Reynolds number area. And then you get actually a reduction in the drag because of that. So it's very interesting. We mentioned all the time that if your flow becomes turbulent, then the drag increases. Yes, the friction increases, definitely. But it can reduce also the area of separation, and the opposite can happen. So the drag is being reduced. There's an interesting example in airplane design. Again, I'm not sure if you like me giving an example on airplane design, but let's say you have an airfoil, okay? You have an airfoil and the flow goes around and then it would like to separate here. So if it separates, that's not very good. because you get buffeting, or eventually the airplane will stall and fall to start. So what they're doing, they're putting here vortex generator, which is going to create turbulent flow. And by creating turbulent flow, this is going to reattach, and you're not going to get that. So it's the same trick what is happening here. If you make the boundary layer turbulent, then you can delay flow separation. On the other hand, that's not a good idea, because when you run the flow to be laminar for less drag, you're going to lose. So I always say that vortex generators on an airplane wing are afterthought, and they are a result of really not doing a very good design at the first time. Anyway, that's just a remark. So I would think that you guys know the Moody diagram, okay, for flowing pipes. You've seen the friction coefficient diagram for boundary layer. And here's another one, which is exactly the same. Okay, so this is another one along the same line, very, very similar. And it has the same message. Here, by the way, we have an additional message, which is this area, which is the critical Reynolds number. Okay, we're almost there. We can start looking at examples. Okay, so I think we did that before, but let me just strengthen the points that we made. So where are we now? Let me just say that, where are we now? We made a model, we solved the cylinder, we understand how the pressure versus velocity is supposed to behave. Unfortunately, there's flow separation, and then the front looks okay of the cylinder, but the back doesn't compare well with what we predicted. So now, based on this understanding and some of the other things we said, let's see how can we make sense out of these stories. Okay, so we need to estimate the drag of this Reynolds number on a streamline shape. Okay, which is a NACA 0012, which is a 12, what 12 means that it's 12% tick. So if this, the length is 1, then this is 12.12, 12%. So if you look at the boundary layer data, okay, and we said 3, 10 to the 6, 10 to the 6, 3, it's somewhere here. Okay, so if I look at the boundary layer data and laminar would be like 0, 0, what did I say? 0, 0, 4 or 3, 10 to the 6. And then this one, the turbulent is going to be somewhere here, is 4, 10 minus 3, okay? So if it's turbulent, we get CD 04 for turbulent. Okay, so that's the point I picked up, this point. Okay, so this is that one on that. And then if I take the laminar flow, this one is going to be 7, 7. And yeah, we're pretty close. Okay, I did do it. Okay, so this point is that one. Okay, I was afraid I'm going to be off. No, it's a good. So we have two numbers. We have number 1, turbulent, and number 2, laminar flow. And so we have two sides for the airfoil, upper and lower. And we have to multiply it by 2. So CD, if we take this one, okay, let's say, then here we're going to have 1.8, but the actual drag coefficient of that one, where do I have that? Okay. Okay, so if I assume that 40%, that's what I'm trying to do, 40% of the drag is laminar, so I take 40% of that one, and then I take 60% of turbulent, that one, 0.27, and then both sides, so multiplied by 2, and then we got 0.054, which is close to the experience. So the story here is that really the flow is laminar and then becomes turbulent, but the drag is a result of skin friction. Okay. This is skin friction. And look at the numbers. The CD numbers are very, very small, okay, because this is an attached flow case. Now, let's look at the pole, okay? So what we have a flat pole, it's a cylinder standing like that. Wind is blowing. And we have the diameter, which is 0.25 meter, and the wind speed is 30, and it's 15 meter high. 15 meter high. We need to find out what is the force on it. Easy. We have Reynolds number. We know what's the velocity. So we take density, velocity, diameter of the pole, viscosity of air. We end up 0.5, roughly 10 to the 6th. We go 0.5, 10 to the 6th. Oh, we are here. Critical range. We are critical range. We're looking at the cylinder. So we need to figure out something in this range. So we're looking at the figure, and then we agree to 0.7. So we think that 0.7 somewhere here, 0.7. We picked up that point, 0.7. Okay, let's say that's the point. And therefore the drag is CD, which we calculated, and the dynamic, and then the frontal area. Okay, so how much is the frontal area? Is the height, and then the diameter. So that's the frontal area, that's S. S. Okay, so we have CD, half rho velocity square, and it gives us 1417.5 Newton. And okay, so then you ask, what would be the moment? Okay, I kind of erased that. What's the moment at the base? So this is the pole, this is the ground. It's 15 meter high. So we think that the wind is blowing equally, therefore the center of pressure at the middle. We kind of speculate about that. In this case, we think the force is going to be 7.5 meter high, divided by 2 times that force. Therefore, the moment at the base, okay, if you want to put the screws down there, you want to make sure that you're going to withstand that amount of moment. Question, coughing, relaxing. Okay, nobody's asking. All right, so this is simply how we play with the drag coefficient. Let's do another one. Okay, so what's the idea is that we have a table for the drag coefficient of cylinder and even for the sphere. And if we know velocity or Reynolds number, then we can actually calculate things. Okay, so here's this is going to be about the formula which I mentioned for the viscous flow. So aluminum ball. Oops, why it ran away from me? Doesn't hold stable. Okay, we have an aluminum ball, 0.5 diameter. So we have some liquid, and we're dropping a little ball here. And then we want to find out how fast it's going down, okay? And this is motor oil, and we know the function. Motor oil is probably 0.3 viscosity, and density is 900 and something. The density of aluminum is 2700. So it's 2.7 times more than water, okay? All right, so let's see. And by the way, here are properties. So that would be density of the oil, okay, 919, and the viscosity is 0.29. That's the viscosity. All right, so we're trying to get a balance on the little ball. So what's happening here is actually the mg, okay? So mg is volume G times density of the aluminum, up acting buoyancy, which is the volume times G, but the displaced oil. Okay, so this force is acting up net. Then the force down, okay, so that's the force going up. There is an additional force, which is the drag. And the drag is one is CD and half rho V, and the frontal area, which is pi r square, okay? So now we have to, we just go through that, and then we think that this is a viscous flow. I mentioned that Stokes suggested, okay, so this is a full range of Reynolds number. We usually say high Reynolds number starts here, something like that. But he developed a formula for, this would be one, so somewhere up to here, for viscous flow, which is 24 over Reynolds, okay? So that's for viscous flow, and we think that that formula will work. Later on, we're going to check out if it's indeed correct, okay? So here we are. So, no, we did the pole. Here we are, again with the sphere. Oh. This is unforgiving, the pen thing. All right, so let's go back. Here is the ball. We figured out the weight minus buoyancy. We have it here. And then the drag, which is going this way, which is CD. Now, instead of CD, we put in 24 over Reynolds. Remember, Reynolds is rho, velocity, diameter, of the 2r in this case, divided by mu, and cancel out everything. We end up with 6 pi u mu. U would be the sinking velocity, u, okay? So then we take this, must be equal to that, okay? And then if we solve that, we end up with u equal that, that's it. So this is equal to that. And why did I end up with r square? I ended up with r square. Okay. Okay. So 6u solved. I'm just checking my own algebra. Okay, hopefully it's correct. Then we end up with this formula. Okay, so that's the thing. Anyway, so this way, mg minus buoyancy, which is the volume times the weight of the displaced liquid. This way is the drag coefficient, which is CD half rho velocity square, and frontal area, pi r square. We end up here. Now we have a formula, we just plug in the number. So 2, okay, 9 comes from the algebra, viscosity of the oil, density of aluminum, density of the oil, G, and then R square, the frontal area. And then we end up with like 0.1 meters per second. So very, very slow. Excuse me. Check the Reynolds number, because we assume that it's going to be in the very low Reynolds number range. Okay. And then indeed, the Reynolds number turns out to be 1.33. So definitely the formula we took, which is 24 over Reynolds, is correct. So that was a good assumption. Okay. So this, we just tried to work with that formula. Okay. Well, let's go on. So we need to learn more about other shapes. I mean, a cylinder is nice. It's a good start, but we were not completely right in terms of experiments. So let's look at other things. So here's some speculation about how can I figure out what would be the drag of a flat plate. So I'm looking at it. Okay, I'm looking at it and just speculating. So velocity comes here and bang, it stops. So Cp here, the pressure coefficient would be 1 because the velocity is 0. Okay, so if I put here Cp, definitely the center is 1. Then I think that on the side, it's probably going to be close to the free stream or something like that. So if the free stream velocity is there, then the Cp is close to 0. So I'm kind of speculating that that's something like that. So turns out actually I'm exaggerating. I think it's falling faster. Okay. And in the back, it's going to be somehow Cp, what is here at that point, pretty much the same here, which is minus 1 point. Again, it's exaggerated, it's too much. But if I do this, then I just play now with the example. So what would be the drag? The drag force would be the pressure on the plate on the front minus the pressure in the back, okay, times the area of the plate. And now it's two-dimensional, so per unit width, okay? So if I figure out what is the average Cp up front, and I figure out what's the average Cp in the back, then just based on the drag coefficient or the pressure coefficient definition, this is the difference. Okay, so P minus P equal half rho V squared. Okay, so that's what it is. And then what is the drag? So I take these guys, substitute it up to his formula, and then I end up with basically C, and the definition of Cp is P minus P and half rho V squared. So we have the half rho V squared here. This one is coming here. And so let's see what the Cp. So at the end of the day, if we want to have CD, we divide by that. We divide by that the D, and we end up with CD. So the non-dimensional numbers are add up pretty much the same way. Okay, so now long philosophy, long talk, what it means. Suppose the average Cp here is going to be, I don't know, let's say 0.5, okay? And this, I exaggerated here, so probably the Cp is more like 0.8. Let's say 0.8. 0.8. Here it is minus, and here it is plus. So the plus is pushing, and the minus is pulling here, so we have to have plus 5 minus 5, minus 0.8. So it gives me like 0.8, gives me minus 1.3. Actually, the drag is 1.2. So I just tried to figure it out. So that is roughly the order of the drag coefficient, which I pointed out here. And then something else is that this is not going to change too much with the Reynolds number because the flow separation is always going to be here. Okay, so it may change a little bit, but not much. So if I look at a flat plate and I say, oh, CD is 1.2, I'm going to be pretty good, pretty accurate. Okay, more than in the case of the cylinder. In the cylinder, it changes with Reynolds number. Here it is not changing because the floor is pretty much separated. Okay, so I'm just copying that and with a little bit example. So let's see. So I came up with a different number. I came up with 0.3, but it's really 1.2. That's pretty much what it is. Very large. That's one of the largest drag coefficients. So let's say that I'm carrying a 1 meter by 1 meter glass plate, okay, normal to the free stream. So here's the glass plate, and the wind is blowing into the glass plate at 15 kilometers per hour, not very fast. So what is the drag? It's CD, half rho V square S. CD, we said 1.2, half density of the air, velocity, meters per second, and then the area, S. Turns out not much, 1.25 kilograms roughly. So it's not much, but here you go. You can calculate that very easily. And this is going to be you're going to compare fairly well with the actual result. Yeah? All right, so now let's try to generalize. So we've been talking, I've been trying to sell you philosophy and all kind of things, but let's get practical. So maybe we can extend those non-dimensional coefficients to a wide range of cases. So what I have here on the left, mostly two-dimensional cases. Okay, let me get the pen. So these are mostly two-dimensional cases or something like that. And then the others are three, but there is, for example, a parachute here. And look at the flat plate. So this is the flat plate. Here it shows 1.17. Now you start adding thickness to that, then the flow separation will go and become less because it reattaches in the bed. Here it's more like this. So the drag eventually, if it's getting longer, the drag coefficient goes down. Very interesting. Okay, this is a rectangular plate, 1.8. They have very similar numbers. Same story here, square, like that, wedge. So this would be very large, okay, very large number, sometimes maybe less. And then different shapes, different two-dimensional shapes. But if you say 1.2, you're doing pretty well. Now this is more streamlined, definitely, than this one, so that the convex versus the concave, it's more streamlined. Okay, so and the flag depends if it's fluttering, if it's moving, it could be, and then that depends on the length. If the length is longer, then the drag goes up. Again, everything is normalized. Remember, CD is the drag and half rho velocity square. And then there is a reference area here, S. So the reference area of the flag would be the flag itself. If I'm looking at a person, then the frontal area of the person. Okay, so this is a side area and this is a frontal area. If I'm looking at the building, frontal area. Look at tree, frontal area. So most of the cases based on the frontal area. Again, aerospace students, anybody here? Wings are based on the top view, not on the frontal area. So in this case, the definition is different. Now you need to check in every case that you're doing how it is calculated. So let's look at this a bit more carefully. So this is just showing a bunch of things. But what is worth remembering is that the 1.2 number is fairly high, okay? And then a complete streamlined shape, let's look at the right-hand side, is 0.04. So it's 30 times difference between streamlined shape, where most of the drag is skin friction, and hey, somewhere here or somewhere with the cylinder. Where's the cylinder? Our cylinder is not here. Something like that, where it's 30, 40 times more drag because of that. Okay, so that is this story. And then we can do examples based on this table. So in terms of problem solving, in the case of the pipe flow, I told you put the Moody diagram under the pillow and try to remember that, because with that you can solve all the pipe flow problems in the world. And this one is in a way similar, because if you look at that, you can try to estimate the drag of something out there, you can find something similar and make a judgment which is probably not too far off. And that's the big advantage of that type of diagram. Now, in this case, in the left-hand side, I did put the lift coefficient. The lift coefficient is defined exactly as the drag, but the drag acts parallel to the free stream, while the lift acts normal to the free stream. All cases here in this, the left-hand side are symmetric. Therefore, we don't expect, there may be momentary because of flow separation side forces, but we don't expect any side forces or whatever we call lift. On the right-hand side, and again, we're going to have special classes on lift later on. But I'm just trying to hint here a little bit that, yeah, if the object is not symmetric, you may be able to generate forces to the other direction. So here is, for example, a completely streamlined shape, 0.004. Lift, of course, is 0. Now, if you make it more like an airfoil shape, but very streamlined, and maybe have a tiny little wheels, and I'm trying to go to automotive aerodynamics a little bit here, then you can have a drag coefficient of maybe close to 0.2 and drag coefficient of 0.15. Now, you go back to the 80s and 70s, they have those really boxy cars, and then they actually had a lift coefficient. All of them had lift coefficient, which is lifting this way, because the flow comes here and then goes around faster on the top than on the bottom. Therefore, pressure lower, you get lift. Very, very logical. So you get some lift, and then we get a drag, which is pretty reasonably high. Then you look at modern cars, they claim to be, so they cannot do much about the lift. The lift is pretty much the same, and then drag coefficients are going down to 0.35. Some companies claim 29, but I don't believe them. Anyway, 35 is a good number for the modern cars. Then those people who want to go faster put all kind of spoilers and all kind of things. They want to reduce the lift. So if you put a little spoiler here, then it's kind of create a little suction under the car, and then you can reduce it to that. But if you do it right, if it's completely parallel, then you're not going to hurt too much the drag. Then some of the racy people put wings in the back and all that, so now it's going to cost you, the drag will go up. But if you do it right, you can have much more flow going underneath the car, which is going to suck the car down. So stagnation is going to be more here, more like that, and then less here. It's going to go as well here. So you may have to generate negative force. Why you want to have negative force? Because you want the tire to stick to the ground more. You want to push more on the tire to increase the friction coefficient of the rubber against the road. Again, race cars do that, and then they can go to -3, but that's cost them almost doubling the drag. Motorcycles, if you lean forward, you 0.8. If you stand up straight like an off-road bike, and the same way, they also have lift coefficient. Numbers for bicycles, okay, we don't have lift coefficient, and then for some of the trucks, trains, and things like that. So we have a whole bunch of array of numbers, and you can somehow navigate between these numbers and somehow figure out what is appropriate for the case you would like to estimate how much. So why you need the drag? Because if something is moving, you want to know how much power requirement is needed. So that's a very important engineering question. So I will go now with examples, and let's try to make them more and more complicated as we go. So we have a billboard. You're building something for movies. Of course, now no movies, but there were billboards. It's 10 feet high, 30 feet wide. Oops, run away. So 10 high, 30 wide. The wind is blowing at it. So go to or something. What is the force on that? And then let's say we have a 50 mile. What do I have? 50 miles? Yeah, I have 50. That's a pretty fast wind. So it has a fast wind, okay? So the drag coefficient, we look at the tables there. You remember I discussed the flat plate, And I said, well, 1.2 is a good number. And then the numbers there is 1.18 or something. Let's take 1.2. So we'll just go to, so let's just go with that number and see what happens. So this is the billboard, 1.2 drag coefficient, 1/2 density of the wear, 50 mile per hour, 1.69 kilometers per hour, 6.3 divide, that's going to make it meters per second. Okay, so now I have velocity in meters per second, square, and then multiply by the area. Okay, so it's 10 times 30, but then 1 foot is 0.3048 meters, so and I don't like, you know, SAE units, so I made everything in metric, and we end up with 10,000 Newton meters. So if I just divide by G, let's say 10, I get 1,000. I get 1 ton, metric ton of force on that. Now, civil engineers, you want to have some sign here with a large billboard. You better design the support here, because that's going to be 1 ton of force acting on it. Okay, so wind forces could be very high. Blimps, everybody have seen blimps over the football game. Of course, now there's no football game because Chargers left town. And anyway, hopefully university will pick up the football game. Let's do the aerodynamics. So the frontal area of this blimp, it's a generic blimp, the one actually stays in Long Beach somewhere. So the frontal area, and you can take the little flips as well. Let's say 58 meter. No, where is the frontal area? Oh, we assume it's 8 meter radius, okay? And then we think the drag coefficient is CD 0.07, okay? And then it goes at 60 kilometers per hour. So I just threw in CD 0.007. So let's just go here, 0.07. So it's between these two, okay? So this would be 0.04, we ended up 0.07. So it's a bit more than this, but less than that. Okay, so it's a good estimate. So we have this, we have a CD, okay? How much is the drag? CD and dynamic pressure area, frontal area is this. We approximated by a 8 meter radius. So it's going to be pi r squared. So CD 1/2 density velocity square pi r squared. Resistance force is that I just cut here, it's 230 kilogram force. That's a quarter ton. It's significant resistance, not so high speed. How much is the power? Is the force to push it, 2,000 that, and then multiplied by the velocity. How much was the velocity? We said it's 50 miles per hour. So it's going to be 51.649. The 1 point here is a point here, divide 3.6. And that's meters per second. You multiply it, you end up that. 1 horsepower. Anybody can help me out? How much is 1 horsepower? Anybody has horses? Anybody is asleep? Anybody awake?
I'll stay here, Professor.
You have a horse?
I do not.
You do not. You know somebody who has a horse?
Yes, I do.
That's good stuff.
What was the question again?
What was the question? What is a horsepower? Okay, and then you have the horse here.
The work done.
Here's the horse is pulling, okay? So he's pulling up 75 kilograms at a speed of to height of 1 meter in 1 second, okay? So it's 75 times G, 9.8. And then it's gonna be multiplied by 1 meter, that's the distance, per second, so it's watt. It's something like 748 watts or something like that. You divide that and you end up with 55 horsepower, okay? All right, so today we don't have too many cars with 55 horsepower, but some of the older cars will have 55 horsepower. That's good enough, okay? That's okay. Let's keep on doing some examples, okay? Cruising automobile, you like cars, okay? We've been talking about cars. So I mentioned a modern car has a CD of 32, a frontal area 1.8, that's pretty much true. 32 is kind of very, so now the car is one of those fancy cars, one is sports cars, 300 horsepower is lots of power. And let's say you're cruising at 100 kilometers per hour, which is like 60 miles per hour. So what is the drag? The drag is going to be CD, which we put 32, which is a good number, actually very optimistic. 1/2 density, velocity square, frontal area, 266 Newton. How much power is needed? 266 times velocity. Okay, times velocity, which is 100 kilometers per hour, about 10 horsepower. So, okay, so the manufacturer says that you have 300 horsepower and you use only 10 horsepower by cruising at, let's say, 55 miles per hour. Now, why do you need that? You need that to accelerate, and you need really to show the neighbor that you go faster. Maybe that's the reason. Okay, and then that's the only explanation. In reality, in the old days, there were cars with 15, 20 horsepower and everybody was happy. Today, you know, you want to go fast, and but you pay for acceleration. You don't pay so much for speed. So anyway, that's a car. A typical car on the highway now going 60, 70 miles per hour, you probably require 16, 17 horsepower. So you don't need much. But if you want to accelerate from that speed, you cannot go faster. Okay, that's the whole point. Anyway, let's look at the race car. Okay, so let's say he's going a little bit faster than your car. Let's say it's going 300 kilometers per hour. 300 kilometers, I don't know, 180 miles per hour, not too fast. That's still reasonable. It has a smaller frontal area, and then we mentioned that because of all the gadgets on it and all that, the drag coefficient is very high. So let's see. So the drag at that speed is going to be the large drag coefficient, okay? And density of the air, speed is faster. So now remember the drag force goes up with the speed square. Before we've been talking 55, 60 miles per hour. Now we're talking 160, 170. So we're doubling or tripling the speed. And okay, so we end up with 4.3 tons, metric tons roughly. Okay, so that's a big thing. So it's significantly more than the weight of the car. Okay, so okay, now you're going to ask me another question, but let me just finish that one. Okay, so then the power required to push that car is 489 horsepower without acceleration, just to keep it going. Okay, so this car definitely needs more power. So now I just said something incidentally, and I probably have to stand by my word. A typical weight for a car like that, anywhere from 750 kilograms to say 1 ton, 1.2 ton, metric ton. This number here is 4 times larger, 4 times larger. So in order to go that speed and do that, the car must have a negative force, which is pushing him against the ground, and eventually the weight or the force on the wheels will be 4 times almost more than the weight of the car. So yeah, this is possible, very uncomfortable, but in a high level of racing, this is happening. So again, this would be CL of -4, which is really unacceptable. But -3 is still acceptable. Anyway, we'll get to the lift later on. So it just showed that now we can calculate number, we can estimate things. Another one, hydrodynamic, a submarine. Cruising at 20 km/h, fairly fast, and then drag coefficient is 0.15. Frontal area is given, and then water density is seawater, so it's a little bit higher than regular water. So it's sort of 1,000, it's 1025. So remember, if it was completely streamlined, it was 004. But now it's more complicated, so it is maybe almost 4 times, a little bit 3.9 times more than that. It has a periscope, it has fins, and it's not smooth and not completely streamlined. So the drag coefficient is somewhere in the 0.15. Okay, so that's where we are. One more time, drag coefficient half rho, velocity square, frontal area is 4. And then we end up with 9. So it is 9 tons. It's a lot of really large force. No, sorry, 900 kilograms. I'm not supposed to touch where was I? Over here. So it's 0.9 tons. So it's 900 kilograms, 950 kilograms. Okay, and the power required, so number of newtons times velocity, 52 kilowatt, which is about, so 5,270 watt, which is 71 horsepower. So if you want to build something like that and you want to select a motor, you're going to need 71 horsepower. That's a way to calculate that. What is next? I have a whole bunch of things. Oh, this is we're getting very close to the end of the class. So what I'll do is I conclude next time. We're going to make the problems more and more complicated. We focus on the drag numbers and try to show that we can actually now solve a whole bunch of practical problems based on the simple models that we have developed. Any questions up to this point? You're very quiet.
We okay, Professor?
You okay?
No questions, Professor.
Did you understand what I was saying? Is it easy to find out?
Yeah, it makes sense, Professor.
It looks
Thank you.
simple.
It makes sense. Okay, so we're going to do more examples, and as we go with the examples, it becomes, I think this is a very nice topic because these are practical problems, and now we can show that we can solve things that may be bothering you, but now there's a very clear and logical way to approach the engineering problem. Okay, so we done that. Tuesday, I'm going to do a shorter class. Most of the class will be devoted to going over material from the past, and we're getting prepared because in a week we're going to have the second midterm, and hopefully everything will go well, and we're all going to be a happy group. So have a good evening and enjoy.